Hello, hello. Hello and good evening, everyone. Welcome to the summary session for Theory of Computation course. My name is Bhavideep Rai. I'm a PhD scholar from IIT Madras, currently researching in theoretical computer science. So, all the sessions for each of the weeks, all the problem sessions for each of the weeks are done, they are over. And now, as the exam is very close, and also to do a brief recap, we'll be conducting a summary session. Okay, and this will be the full and final session for problem solving sessions of this course. So, this will be the final session. Now, yeah, as the name suggests, we'll touch up all the topics that we covered throughout the course, okay, one by one, and we'll do it in a very a top view, okay, a high level view fashion. So we would not be going very deep also, but I'll be going from the beginning in the order in which the course was taught, okay, and almost in the order, okay. Some of the things, now that we've gone through the entire session, I'll be talking about a few of future sessions also, and how they are interrelated with each other, in which you'll have a better understanding, okay. Now, so and on the way, I'll be giving you several examples so that you get what I'm talking about more properly. Okay. So now that I've said that, let us begin. So let me start beginning with the title of the subject itself, Theory of Computation. So what is theory of computation? It is the study of computation. And what is computation? It is any process, any non-trivial process which helps in solving a problem. Okay. So whatever a computer does, right? It helps you solve a problem. And theory of computation talks about, you know, whether it is possible to solve a problem at all, and if it is possible to solve a problem, then how quickly can we solve a problem, okay, and what are the classifications of such problems, okay, and what are the machines which solve those problems, okay, and these are all the questions that theory of computations addresses. And yeah, hi Bhuvana, welcome. Okay, so yeah, so I'm doing the summary session where I'll be touching on all the topics one by one, okay, and if you have any doubts in between or right now, you can let me know. I'm audible, right? Hi, good evening. Yeah, okay, good. Thank you. Okay. So, okay, good. So, let me know if you have any doubts in between. So, I'll be going across each particular topic one by one, okay, and we'll be looking at from a high level viewpoint, and I'll give you examples one by one. So, as I already said a minute earlier, theory of computation, okay, involves deals with uh, computation. What is computation? Computation is the process of solving problems, okay, and therefore the questions we are interested in is are like, whether it is ever possible to solve a problem, whether what is the best way we can solve a problem, okay, that is what complexity addresses, and what if we are to solve the problem, then what are the type of machines we can use, and what are difficult problems, what are hard problems, and so on. So formal language theory, okay, this is one part of theory of computation, and formal language theory talks about, languages, you know strings, languages, okay, grammars, and properties of those languages, and so on. So it is a separate study as it is, okay, and these are interconnected. So what is computability theory? It asks about impossibility, okay. It talks about impossibility of solving problems. that is um, do unsolvable or undecidable problems exist. So this is what computability theory talks about, and complexity theory talks about um, it says, okay, fine, we know how to solve problems. We know that a particular problem is decidable, that is, it can be solved, and how efficiently we can solve it. In terms of, say, time, space, etc. Okay. So, yeah, we'll look at the first one. Okay, now, formal language theory. So, formal language theory, just to recap, an alphabet is a set of symbols, okay, which is often denoted by sigma. For example, 0, 1. Okay, so this set 0, 1 is an alphabet. This set 1, 2, 3, 4, 5, 6, 7, 8, 9 is an alphabet. And A, B, C, D, and so on till Z is an alphabet. Note that they are distinct from each other. You cannot have two symbols that are same. And also, it needs to be that the alphabet is finite. The set is finite. Okay. Next, string is a sequence of letters or symbols from sigma, taken from sigma. For example, 0, 1, 1, 1, 0, 1, 0. So what is this? This is a string over an alphabet sigma where is equal to 0. For example, APPLE, apple. So this is another string, and this is over, say, sigma equals A to Z. So as you can see, even the words we speak can be categorized into strings and alphabets and so on, right? I mean, that is how it is addressed. Okay. And sigma star is what is known as closure. Okay, this is what is known as clean closure of sigma. So take the set sigma, okay, for this case it is 0, 1, okay, and try to derive all possible strings from it. Okay, one possibility is you pick a 0 first, and then you pick a 1 first, then you pick a 0 first, then a 1, and so this is one example. Another example is you pick a 1 first, then 0 first, then 1, then 1. Okay, you keep picking this and form a string, or you pick nothing. In that case, what do you get? An empty string. Okay, so you pick either nothing or a bunch of symbols and arrange them, okay, and then you get a string. So that is the composition of what sigma star is. It is all the strings that you can form from 0, 1. Okay, so here example, we have sigma, we have epsilon, which means I pick nothing. Then I have 0, then I have 1, then 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1. Anything you can form from sigma is basically sigma star. Okay, now what is the language? Okay, so this is anything that any string over sigma, over the alphabet sigma, including epsilon, empty string. Okay, now what is language? A language is a set of strings. Okay, but if that set is of strings, okay, takes symbols from the alphabet sigma, then it is nothing but a subset of sigma, right? Because any set of strings you take will always be a subset of sigma star, because sigma star consists of all possible strings over sigma. So example is, say, 0, 0, 0, 0, 0, 0, 0, 0, and so on. This is also what it can be also written as 0 power I, where I is at least 0. So this is an example of a language. It is a subset of sigma star, right? I can only pick 0, and later I see a 0, 0, I'll pick that, and so on. 0, 0, 0, I'll pick, and so on, right? So it is a subset of sigma star, any language. Okay, and another example is like 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, and so on. This is another example. And this can also be written in a compact form. It is not always possible, but 1 0 I 1 such that I is at least 1. So this can be written as follows, right? So this is what a language is. Next, uh, now we'll talk about languages, but at the same time we'll jump to machines. Okay, quickly. So there are machines that solve these computational problems. Okay, and the types of machines are what are called are at least the ones which are discussed in the course are finite automata. Okay, and they are of two types: DFA, NFA. DFA is deterministic, and NFA is non-deterministic. Okay, non-deterministic. Oh, okay. Computable, decodable. Okay, okay, Bhuvan. I'll first quickly go over this. Okay, then we'll discuss that at the end of. Okay, okay. At least until 7, I'll complete from here, and after 7, let's do those questions. Is that fine, Bhuvan? Okay. After 7 p.m., I'll address your questions. Okay, fine. Okay, fine, good. Um, so we have push down automata, then okay, push down not okay. So push down automata is also of two types, DPDA and NPDA. And so what is the difference? Okay, so then we have Turing machines and so on. So what we are trying to do is we are trying to make the machine model, okay, stronger, stronger and stronger. That's what we are trying to do. And how are we making it more strong? Because first I have very small amount of memory, okay, constant size memory. Order 1 means constant size. Next, I'm giving it a stack. Now what is stack? It is a restriction where I can push from the top and pop from the top. I can keep inserting elements from the top and remove only from the top. And next I have a tape where I can insert, delete, do whatever anywhere on the tape. So I'm making the machine stronger and stronger. So the idea is that as I make the machine stronger and stronger, I'll be able to decide more and more languages, harder and harder languages. So that is the idea. And the language of a machine is the set of strings which is accepted by it. Okay. Now, so this is the correspondence which is very important. Keep this in mind. Okay. A DFA or NFA, okay, is equivalent to regular languages. Okay, sorry, the language it computes are regular languages. Okay, are what are called regular languages. And DPDA, or deterministic pushdown automata, is what is called DCFL, but this is not focused in the course. We are only, as soon as we talk about PDA, we are going to mean that it is non-deterministic. Okay, and an example of that is CFL. Yeah, sorry, the language it computes are what are called CFLs, context free language. Context free language, and this is equivalent to CFG, context free grammar, or it is a type of grammar which computes this. And recursive and are those languages computed by, okay, these are languages, these are machines. Recursive are those languages where computed by total Turing machines, where total means that the machine halts always halts given any input. Okay, and recursively enumerable means that the Turing machine need not halt always. Okay, Turing machine halts only on yes instance. Okay, so this is a very important diagram, always know this. So this regular language is contained inside DCFL, okay, and DCFL is contained inside CFL, and CFL is contained inside, oh no, okay, I made a mistake. Okay, the machines are towards the left. Okay. Okay. So recursively enumerable should be here. Recursive should be here. Sorry for the confusion. Recursive and recursively enumerable. And recursively enumerable are Turing machines, and recursive are total Turing machines, and total Turing machine means always halts. Okay. Okay, and there are languages above this also, and those that form sigma star, not sigma star, sorry, power set of sigma star. Okay, so yeah, before I move on, so this is another exercise problem. So question is, okay, how many languages are there over sigma star? Okay, how many languages are there over sigma star? So what does sigma star look like? Sigma star is like this epsilon 0 1 0 1 0 0 1 0 1 1 1 and so on, keeps going on like that, right? And what is language? It is a subset of sigma star, right? And so it is for example, I can choose epsilon 0 1 1 0 as one of my language. This is one language, and another language is 0 1 0 0 1 1 1. And I can even take infinite languages by choosing infinitely many elements from this object. But if each language is a subset of sigma star, and every subset of sigma star is a language, how many languages are there over sigma star is nothing. The answer is nothing but the number of subsets of sigma star, right? So number of languages over sigma star is nothing but the number of subsets of sigma star, right? So given any, so there is a simple formula for this. Given any set of size n, number of subsets equals to pi. So what does mean? Number of subsets equals 2 power size of sigma star. Okay. Now similarly, okay, set of all languages. I take every possible language over sigma star. Set of all languages over sigma star is nothing but set of all subsets of sigma star. Set of all subsets of sigma star. So, do you know what this term is called? What is the term for the set containing all the subsets of that set? So, what is the set? Okay, for any set, okay, the set of all its subsets is called the power set. For example, if S is 1 2 3 4 1 2 3. Then power set of S is empty 1 2 3 and 1 2 2 3 3 1 3 1 2 3 and so on. And anyway, this is how it goes, and the size of the power set is 2 to the size of the set. That's how we got the previous one. So power set of sigma star. So this is another way how we got the power set. So the set of all subsets is the power set of sigma star. Okay. So any language you take is actually an element of the power set of sigma star. Okay. Because power set is nothing but the set of all subsets, and each subset is nothing but a language. Okay. Is this fine, Bona?
Yes, sir. Understood, sir.
Okay, good. So always remember the set of all languages over sigma star is nothing but the power set of sigma star. Okay, so that's why I was saying that you have this hierarchy where regular language is contained inside DCFL is contained inside CFL, and CFL is contained inside recursive, which is contained inside recursively enumerable, and so on and so forth until power set of sigma star contains all these things, because all these are sets of languages, and sets of languages are nothing but subsets of power set of sigma star, because power set of sigma star contains all the languages possible. Okay, now good. So that's about languages and so on. So here's a quick recap on what a DFA is. Okay, so a DFA is a machine, okay, which has q sigma delta q naught f. Okay, q is a set of states, always finite. Remember, a DFA always has finite number of states. Okay, and sigma, okay, is the alphabet over which the DFA works. Delta is the transition function, okay, meaning on a particular state, if you see an element from sigma, then where do you go? The next state, and then you go to a start state. And then you have a start state where your computation begins, and f is the set of final states. And what is the acceptance condition? If at end of computation if at the end of computation, what happens? Some q in final state is reached. Some final state is reached. Okay. Now I'll give an example. Here is your language. Okay, here is your DFA. Let's say q0, and q0, on seeing a 0 it moves to q1, and seeing another q0 0 it moves to a q0, and then seeing a 1 and seeing a 1. Question is, what kind of strings does it accept? Okay, and this is this, and this is the final state. Okay, and question is, what is the language of this? So can you tell me the language of this, Bhuwana? I mean, you can take a guess also. What are the kind of strings it will accept?
What?
Yeah.
001.
Okay, let's see. You said
Zero.
oh,
Yes.
what are the strings again?
0 0
0 0.
triple zero, sir. 0 0 0 triple zero.
Oh, but how triple 0 0 is triple 0 cannot be accepted, because if I do
Yes, sir.
zero
Yes, sir.
zero zero, then it will go to a non-final state. I need to land in a final state.
Yes, sir. Q1 is the final set. Now only same, sir.
Oh,
Double
okay.
zero, right?
Double 0
Then 1 0 0.
1 0 0
0 1 0.
0 1 0
Double 1
double
double
1
0.
double 0
0 double 1 0.
0 double 1 0. Good.
So many, sir.
Yeah, and so on. Can you go with a very long one? Can you try a very long one?
Um, 1 1 1 1 1.
1 1 1 1 1
0.
0
Again 1 1 1 1
1 1
0.
1 0.
Um,
Good.
yes, sir. That's it, sir.
Can we go longer?
Um,
I mean, continue with this 1 1 1 1 0 and
again 1 1 1
okay. Then
0 1 1 1 0.
0. Yeah, right. 1 1 1 0 and so on. Right.
Yes, yes, sir.
So what we see is actually okay, to be accepted. As soon as I see a 0 in the beginning, okay, to be accepted, I can get several ones, or I can not choose ones, okay, but definitely I'll have another 0 following it in order to reach the accept state. As soon as I go to a 0, to reach an accept state, I need to choose a 0. Getting it? Sometime or the other. If I see another 0, then after going 1 1 1 1 1, I need to get to a 0 in order to reach Q0 once again, the final state. Right? So, what is actually happening is this state, okay, this state is representing even number of zeros, and this state is representing odd number of zeros. Okay, this is representing even number of zeros, that this one is representing odd number of zeros. Now see, if I have example, let's say the string I have is 0 1 1 0 1 1 0 1 0, okay, and I'm claiming my language is okay, my language is um, I'm claiming my language is the all the w such that w has even number of zeros. Okay, so now what do you have? So 0 1 0 0, I'll go 0, then a 1, then 1, right, then a 0, then a 1 and a 1, then a 0, then a 1, then 0. Every time I see even number of zeros, I'll land at Q0, and as soon as I see another 0, this is, I don't want to accept it, so I'll use another state for that. This state represents odd number of zeros, so I'll go here. Then after that I see a 1 here, then I'll keep staying in that state because I've still seen only an odd number of zeros. To see an even number of zeros, I need to as soon as I see an even number of zeros, I go back to this state, which is the final state. This makes sure that I have only seen an even number of zeros. Anytime I see an odd number of zeros, I am always going to Q1. Okay. So what is the language of this machine? The language of this machine is all the strings which has an even number of zeros. So for example, if you try x equals 0 1 0 1 0 1, this has an odd number of zeros. So what happens? 0 1 0 1 0 1. So I stay here. I don't accept because this is a non-final state. Okay. But if I had even 1 0 here, a single 0 here, as I was staying in this state, as soon as I saw this 0, I shifted to this as my final state. Okay. Please also explain how PDA transition happens with an interactive example having epsilon transitions. Okay, sure. Okay, sure, Sashi. Will do. Okay. Okay, so yeah, but the important fact is, okay, the important fact, okay, sorry, the important fact is in designing any DFA, use states to remember. This is the way to go, huh? Always. If you need to, because DFAs has so little memory, to remember anything, you need to use states. Keep that in mind. Okay. And okay, I'll give another example of a DFA. So let's think of a slightly non-trivial example. Yeah. Okay. Actually, it's not a non-trivial example, but okay. Let's say begins uh, with 0 1 0 0 1 0 1 0. All strings that begin with 0 1 0. Okay. Key thing is you need to use states to remember. Okay. So for example, here I have a state. Okay. So the construction is as follows. Okay. What I want to do is before I say this, any string I see will be of this form 0 1 0 followed by something something. 0 1 0 followed by something something. Okay. So any string, I need to first see a 0, else if I don't see a first 0 in the beginning at all, then the word does not belong to the language at all, right? So next I'll see a 1, okay, then move to another state. I'm not happy yet, I need to see another 0 to be reassured that okay, fine, I am I have seen 0 1 0. Okay, as soon as I see a 0 1 0, I reach here. Okay, and then what do I do? If I see anything else, and this is the final state, if I see anything else, I am reassured, I'm guaranteed that oh, in the beginning I've seen a 0 1 0. So even if I see a 0 or 1, I still stay here. Okay, so and yeah, a DFA should have transitions on all symbols. Okay, so therefore I make an extra state which is called the dead state. Okay, and there, if I see a 1 in the beginning, I know definitely this word does not belong to my string because it is beginning with a 1. I should begin with a 0 1 0. If I see a 1, then I go here. If I see a 1, I go here. And this is what is called a dead state. And a dead state means it's a useless state in that sense. Okay, this is another example. And okay, another question is, so here is a DFA which accepts only those words which are the even number of zeros. What kind of change can I make here that I'll accept only even number odd number of zeros? This is a DFA. Can I make a change to this DFA so that I'll only accept odd number of zeros?
Q1 is final state, sir.
Make Q1 as final state. That's right, correct, good. So, okay, so if I make Q1 as final state here, then I'm done because I'll also make Q0 as non-final state. And because as soon as I see a 0, the same logic holds, right? As soon as I see a 0, I get odd number of 0 and then and I go here and I see another 0, it means I've seen even number of 0, so I go to a non-final state and so on. So another important point is that it is not just for even and odd. Okay, if M computes L, okay, M prime computes L bar, the complement of the language. What is the complement? It is, sigma star minus L. So all the strings, because sigma star contains all the strings which are over sigma, and I'm removing all the strings that are there in L, so whatever it remains. So for example, sigma consists of all the binary strings, right? And from there I'm removing all the strings which have even number of zeros. If I remove all the strings which have even number of zeros, what will I be left with? All the strings which have odd number of zeros. So for that particular L, our L bar is this. L bar is the set of strings which have odd number of zeros. So M prime computes L bar. Okay, there exists an M prime computes L bar such that M prime is nothing but M with final and non-final states interchanged. Okay, so it means, what does this also mean? It means if L is regular, what is regular? Regular means there is a DFA for it, okay, if or NFA for it. If L is regular, then L bar is also regular. Why is L bar also regular? Because I can always construct a DFA by switching the final and non-final states. And if I switch the final and non-final states, and then I get a DFA, since there is a DFA for L bar, it means L bar is regular by definition of regular language. Okay, good. Okay, now I'll do non-deterministic DFA, and Sashi, I'll reach PDA soon, and then I'll explain that. Okay, transition happens with an interactive example having. Okay, good. Okay. Okay, so what is NFA? Okay, I'm just, so NFA is nothing but similar to DFA. So the entire, I can copy this, okay, from, okay, I can copy this definition from DFA, paste it here. I'll copy this entire definition. It has the same set of states, alphabet and transition and start state and set of final states and so on. Okay, there's only one difference. Okay, and that difference helps us a lot in designing automatons. Okay, and that is that a DFA will be like this, that on a 1 it will move somewhere, on a 0 it will move somewhere, right, on another state. So Q1 and Q2, let's say this is a DFA, and NFA okay, Q1, Q2, and NFA can actually move to multiple states on seeing the same symbol. So for seeing, for example, seeing a 0, it can move to Q3 also. For example, seeing a 1, it can move to itself. You see it? So on seeing say 1 1, okay, it can either move to Q1 or it can choose to remain to Q0. How? It'll see a 1, then it'll see a 1, then it'll go to Q1. Else what it can choose to do is it can choose 1 and again choose a 1. Okay, on seeing a 0, it will move to Q2 and Q3 at the same time. So this is what non-determinism means. Determinism or deterministic means I can, given the current configuration, I can always predict the next configuration. Okay, and non-determinism means that given the current configurations, there are several possibilities. Okay, that is what non-determinism means, and therefore since I can move to a bunch of states, the transition symbol, okay, for example in the DFA case, the transition looked like this. On Q0 on seeing a 1 will move to Q1, Q0 on seeing a 0 will move to Q2. Okay, now in the NFA case, Q0, okay, on seeing a 1 can move to itself as well as can move to Q1. And similarly in this case, okay, you see on seeing a 0 there are two possibilities, Q2 and Q3. So Q0 on seeing a 0 can either move to Q2 or it can move to Q3. So you see that there is a set, right? Therefore the definition here changes. The function, instead of taking a single state and a single symbol mapping onto a single state, it can map to a bunch of states. So what are the set of it? It'll give a set of um, a set of states. So what is the set of states? The power set of Q. Okay. What is power set of Q? Look, Q is, this is my Q, no? Q0, Q1, and so on. What is power set of Q? Power set of Q is like Q0 or MT or Q0, Q1 or Q1 or Q0, Q1, Q2, Q1, Q2, and so on. I'm choosing one guy from here. I'm choosing one guy from here. For example, here, see, I chose a Q2, Q3. No, somewhere there was a Q2, Q3, and that is what my transition function output. Before it was just choosing a single state at a time in the deterministic version. So this is the only change here. So I'll highlight this. This is the only change here. Now, quickly, so DFA and NFAs are equivalent in power. Okay, what does that mean? What does that mean? DFAs compute regular languages exactly. It cannot compute something stronger, okay, or weaker. And same with NFA. How was this shown? Every NFA is a DFA, right? Instead of choosing, instead of considering these kinds of sets, instead of considering these kind of sets, large sets, if I consider only singleton sets, if I just change this, if I do this, then it's nothing but a DFA, it's nothing but an NFA, right? This DFA also qualifies as an NFA. All I'm doing is the transition functions. I'm making sure that the transition function only maps to a singleton set. That is a set containing only one state. So it's still an NFA. And NFA is a DFA. So that there is no problem. And given DFA, I can make sorry, okay, what am I saying? Every DFA is an NFA, and given an NFA, but the other way around is not clear, right? Because see, NFA seems much more stronger because it has this parallelism property, right? It can move to a bunch of states at once. So given an NFA, it can make I can make equivalent DFA. How is this done? This is done by a way called subset construction. And you must have seen what subset construction looks like. I'll just tell you a gist of it. It means if I have a NFA, which is Q, sigma, delta, and so on, F, and so on, right? If I have an NFA like this, what I'll do is, and if I'll what I'll do is I'll draw all possible sets. So draw a DFA with 2 to the size of Q states, and each of the states will actually correspond to the subsets. Okay, so 2 to the Q states. Why? This is nothing but the power set of Q, which looks like something like Q0, phi. Okay, first phi, let's write phi, Q0, Q1, and Q2, and say Q0, Q1, and Q0, Q2, and so on. What is the size of this? size of power set is the 2 to the power size of the states. That's why size of power set of Q is 2 to the power size of Q. And what does this represent? What does this represent? This, each of these states, okay, now consider each of these sets as a separate state. Okay, now this particular state represents that I'm moving at Q0 and Q1 at the same time. Okay, for example, here on seeing a Q0, I'm moving to a Q1 as well as I'm moving to itself, right? So it will look like something like this. On seeing a 1, Q0 can move to itself, or it can move to a state, it can move to a state itself as well as Q1. And on seeing a 1, what is happening? On seeing a 1, it is moving to Q2 as well as Q3. Sorry, this is not there. This is taken care of. On seeing a 1, we can move to both Q2 and Q3 simultaneously. This is what it represents. And finally, we'll just make the final states. And what is the acceptance condition of a non-deterministic automata? At least one of the final state we reach is final. So what is the final state in this particular construction? At least one of the, for example, let's say Q0 was final, then this entire state will be final and this entire state will be final, because at least it means that at least one of them, because it contains Q0, it means at least one of the paths will actually lead to Q0. Okay. So and you can see that this is deterministic. This is completely deterministic. On seeing a 0, it will move to a single state only. On seeing a 1, it will move to a single state only. Okay, good. And okay, that is about NFA. Okay, and why are NFAs useful? Particularly, it is helpful in designing automatas for languages. For example, here is an automata. Okay, here is a language W such that W ends in 101. Okay, it ends with the string 101. We saw how to do begins with 101. Okay, but what is the problem here? Begins with 101 was simple. 101 followed by something. So I have a state for 1, I have a state for 0, I have state over 1, and then I'll just accept trivially come 0 or come 1. Okay, but something 101. If I do the same logic, okay, I let's say I keep states and so on, and then I see a 1, then I move to another state, and then 0, then I see another state, and so on. But thing is, I do not know where the string ends. Okay, so here is the idea. So one way to design a DFA, it is possible to design a DFA for this also. Okay, the idea is if I see a 1, then I see a 0, then I see a 1, then I land in the final state, and if I see another string, it means I have not seen the end yet. And if I see, for example, a 0, I move to this state. Sorry, if I see a 0, then I move to this state. If I see a 1, then I move to some other state, and so on. But all this hassle is not there. All I need to do is come 0 or 1, I stay in Q0, and 1, 0, 1, and this is the final state. Take note, this is an NFA clearly, because on seeing a 1, it is moving to this state as well as this state. Okay, on seeing a 1, but okay, it's seeing a 1 as well as 0. Yeah, but the idea here is that this DFA, this NFA will accept only if this is reached, and this guy is reached only if I make a non-deterministic guess here on 1, and after this, if I see anything else, I'll reject, and it means that I'll only accept those strings which end in 101. Okay, for example, if I see 1 0 1 1 0, okay, So in a particular non-deterministic guess, okay, what I'll do is I'll just see 1 0 1 1 0 and so on. I'll end here and I'll not accept. Another possibility is I see a 1, then I see a 0. Okay, I chose this branch, okay, instead of going here. I see a 1, then I see a 0, then I see a 1, and then I see a 1 1 0 now. So I'll reject. It is implicitly understood that if I don't have a transition, I'll move to a dead state, so I'll reject. Okay, and so on and so forth. But this string will never be accepted by this NFA. The only kind of strings that will be accepted by NFA is of this form, something 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 101, because even though I might get confused because my computation may be 0 1 and so on, and then move this path and so on, or I might even end here, it is enough that in one of those non-deterministic guesses I land up in the final state. And that is exactly when I keep looping on Q0 for all these parts, and then I'll choose a 1, then a 0, then a 1. This is enough. Okay, so this is an example where NFA is very simple, especially when the language is something like W, and W ends with 101 at the third last position. NFA is particularly easier to design in this case, but it's not more powerful. We already saw it. Why? Okay. Now, closure properties. Regular languages are closed under union. Okay, and how do you do this? You do this using subset construction, the way you did NFAs. Okay, you basically do 2 to the power q many subsets. Okay, and okay, first of all, what is union? Okay, L1 consists of all W. Okay, L1 is a language. Okay, L2 is a language, and L1 union L2 consists of all the W such that W is either in L1 or W is in L2. So it means on running the machine for L1, okay, and L1 L2 both are regular. Okay, on running the DFA for L1 for W, I should reach the final state, or on running on the same W for the machine for L2, I should reach the final state. So the idea is I do the subset construction once again, okay, and then I assume that I am moving in the states of L1 as well as L2, okay, sorry, the states of the machines for L1 and L2 simultaneously, and if at any point I reach the final state in either L1 or L2, I'll always accept. Intersection is also the same thing. If I reach both the final states, okay, of L1 and L2, then I'll accept. Complementation, we already saw that if we interchange final and non-final. Concatenation is as simple as this. I take the NFA for L1, okay, then the final state for L1, I'll concatenate it with the start state of the NFA of L2, and then it'll have its own final state. Concatenation is what? L1 and L2, then the L1 concatenated with L2 is nothing but, okay, the set of all W1 concatenated with W2 such that W belongs to L1 and W2 belongs to L2. This means I take some 0 1 1 from L1 and 1 0 1 from L2 and combine these to form 0 1 1 1 0 1. This should be in the L1 concatenated L2 language. Okay, and clean star, we already seen what sigma star is. We do this concatenation process several times, and from the same proof you'll get clean star also. So under clean star also, so it's this L1 star, you keep concatenating with itself. By 4 itself you get clean star. It is okay, it is closed under regular regular languages are closed under these 4 things. Okay, in case but I did not tell what closed is. Okay, closed means that on doing this operation I'll still be regular. Okay, so on doing a union between regular language I'll still be regular, on doing intersection I'll still be regular, and so on. Okay, tell me if that was too quick. Okay, I'll move to the next part. otherwise. If you have any questions out here, I'll move to the next part. So next part probably, yeah, that yeah, Bhuvani, you were saying something?
Sir, homomorphism language, sir.
Okay, okay. Homomorphism, is it there in the? Are you sure this is in the lectures?
No, sir, we have an UG syllabus, sir.
Ah, okay, okay. Yeah, homomorphism. So it's not in the. Yeah, it's not in this course. So I would not. But okay, anyway. Um Homomorphism is an idea of substitution. So what you want to say is. So what you want to say is. You have, okay, you have two languages, okay, L1 and L2, okay, and L1 is over some alphabet, say 0 1, and L2 is over some alphabet AB, okay, and we say phi is a homomorphism, okay, and this is sigma 1 and sigma 2 from sigma 1 to sigma 2. If, okay, and if, first of all, if W is in L1, okay, not exactly sigma 2, it's from L1 to L2. Okay, if W is in L1, if and only if phi of W is in L2. Okay, now what does this mean? What does this mean? So what does phi do? Phi is defined as follows: phi of, okay, AB is equal to phi of A, phi of B. This is the first property, and the other property is phi is a bijection from W from sigma 1 to sigma 2. Now, what does this mean? For example, if I have 0 1 as one set and AB as another set, 0 maps to A and 1 maps to B, okay, and 0 1, phi of 0 1 is nothing but phi of 0, phi of 1, which is A B. Similarly, if you, so using this rule, if you have 1 0, it is nothing but B A. So if you have phi of 1 1, it is nothing but B B, and so on. What you are seeing is that using this map, okay, so you can extend this homomorphism from sigma 1 star to sigma 2 star. So sigma 1 star looks like this, okay, it looks like 0 1 0 0 0 1 1 0 1 1 1 1 0 0 0 0 0 0 1, and so on, and it will map to sigma 2 like this. 0 maps to A B A A A B B A B B A A A A B, and so on. So you are essentially renaming the alphabet. The idea is that, okay, the idea is that now what is the main homomorphism telling? On taking your W in L1, if and only if on doing this particular map, you are transforming the alphabet from 0 1 to say AB. Okay, you are transforming the alphabet from 0 1 to AB. Then it will still be in L2, and this is true for all W. For all W in L1, for sigma star, sigma 1 star. Take any word in L1 on doing this transformation and changing from 0 1 to AB. Okay, it's not necessary that the alphabet is 0 1 and AB, it could be other alphabets, but you get it right. On doing this kind of mapping, if the original word is in language L1, then the the other word, the word that you are mapping, okay, the phi of W will necessarily be in L2, and the other way around also. So what does this say? This means, so there exists an homomorphism from L1 to L2. That is what you are saying. That is what you mean. And regular languages are closed under homomorphism. Okay. So on doing this mapping, okay, and I give you you have a regular language, I give you a phi, okay, and then I tell you to map to another string, another set of alphabets. Those alphabets together will also make a regular language. Okay, understood, right? Okay, good. So the relationship it gives is, if L1 and L2 have an homomorphism between them, then they are in a sense similar to each other because they are same up to renaming of variables. Okay. So okay, a nice idea would be, so if my language is of this form, okay, let me think for a while. Okay, a non-trivial example, I'm not exactly getting that, but okay, if my language is of this form, okay, 0 1 okay, yeah, so here I have it. Yeah, L is 0 to the I, 1 to the I, okay, 0 to the I, 1 to the I, where I is at least 1. This is L1. And L2 is 0 to the J, okay, 0 to the, give me 1 minute. Okay, L2 is 0 1 to the J and 1 0 to the J. J is at least 1. Okay, these are the languages I have, and claim is L1, okay, claim is L2 is regular. Let's say you don't know that L2 is regular, and but L1 is definitely regular, right? This can be done by RDF. Oh, wait. No, sorry, this cannot be done by RDF, but I'll just, okay. This cannot be done by RDF. This is a context-free language, but it's okay. I'm just trying to explain homomorphism, right? So regular is not important here. What is homomorphism here? So what I meant to say is there exists a homomorphism from L1 to L2. Okay, and what is the homomorphism? Phi of 0 is equal to 0 1 and phi of 1 is equal to 1 0. Okay, and suppose L1 were to be and you can check it actually. So all the 0 will map to, by that rule homomorphism can be split, okay, and by that rule all the zeros will be transformed into 0 0 1 and all the 1 will be transformed into 1 0. So since regular languages are closed under homomorphism, you can say that, oh, okay, so these two languages have a homomorphism between them, so or L2 is homomorphic to L1. Oh, then I can say that if L1 were to be regular, then L2 is also regular. That is an application of this. Okay, if L2 is, let's say, a very complicated language, you don't know whether it's regular or not. In this case, both of them are not regular. These are context free. Okay, but anyway, if this were to be regular, then I would have said that this is also regular. So that is the application of homomorphism and closure under homomorphism. Okay, that is clear. Oh, okay. It seems that Buana has left the meeting. Okay. But I think he'll come back probably. Okay. Anyway, so yeah, Sashi, I'll take your question now. Sashi, you're there, right? Hi, Sashi. Hello. Oh, okay. Sorry, I'm seeing your message right now. Sorry. Okay. Yeah, I'll take your question now. Okay. Um, okay. Your question says, please also explain how PDA transition happens with an interactive example having epsilon transitions. Having epsilon transitions. Um, okay. Let me think. Okay, Bhuwana is also there. So Bhuwana, I had explained a little bit more on homomorphisms. Okay. So, oh, okay, he has left again. I think he has some internet problems. Okay. Anyway, um, okay, let's do an example on PDAs. So PDA is nothing but a DFA with a stack. Okay, PDA is nothing but a DFA with a stack. Now, the transitions are bit special in the form that we look at the top of the stack and then tell what kind of operations we do. So, okay, let me think of an example. So, here is a language. Okay, here is a language. Um, A to the I, B to the J, C to the K. Okay, first I'll do a simple one. E to the I, B to the J. Okay, A to the I, B to the J, and I is at least I is at most J. E to the I, B to the J, I is at most J. So here's the idea. Okay, A, B, 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 B. So here's one input, and here's another input. So this is a good input. This is a bad input. Okay, this is a good input. That is a bad input. Now, the idea here is, I'll start seeing A's, then I'll start seeing B's, but I have a stack. That is my advantage. Okay. Idea is I'll keep pushing onto the stack as I see A's. Okay. There's a dollar sign on the bottom. Okay. There are two ways to accept in a PDA. One is by empty stack or by reaching the end of the string. Let's do the empty stack approach. Okay. So as I saw an A here, I put an A here. Next I saw another A, I put another A. Next I saw another A, I put another A. And I saw another A, then I put another A. Okay. Now I've added 4 A's to the stack. Now I'm starting to see B's. What I'll do is for every A that I see on the stack, I'll start popping B's. Okay. So I see a B, I'll pop. I see another B, I'll pop. I'll see another B, I'll pop. I'll see another B, I'll pop, and my stack is empty, I'll accept. By empty, I mean I see a dollar sign. Okay. Next, let's see the non-example. That is A, B, B. This should not be accepted because number of A's are more than number of B's. So if I see an, again same thing, I'll start with a dollar sign. Okay, I see an A, I'll push. I'll see another A, I'll push. I'll see another A, I'll push. I'll see another A. I've reached here. Now I see two B's. So I'll pop for the first B and I'll pop for the second B. And note that I've not seen a dollar sign. So, and that means I've not emptied the stack. And that means the the PDA rejects. Formally, how do I show it? Formally, how do I show it? Here is Q0. Okay. And if I see an A, and on top of the stack, let's say there is a dollar sign. Okay. Then what do I push on top of the stack? I'll push the same dollar sign as well as an A. Okay. I mean, see, there are several, by the way, there are several ways to denote this. Okay. There are several styles of transition. In this style, what I mean is if I see an A in the input string and I see a dollar on the top of the stack, then I'll remove the dollar and then push dollar and A once again. Okay. Another way which is shown is, I think this is how it's done in the lecture is, if I see a W and a dollar, which means this part is W of the stack, then I see a dollar. Okay. What it means is if I see a W, then a dollar. W is a string. Okay. Then what I'll do is I'll push W as well as dollar as well as A. This is another way to do it. And or some people don't keep W, they'll just keep dollar and A, which is understood. So there are, what I'm just saying is there are many ways to denote this. This is not the only way. Okay. Okay. So this, what does this mean? This means I've pushed A. I've seen a dollar, then I'll keep the dollar as it is and then push an A also. Okay. Now, as long as I see an A, I'm good, right? So another possibility is I see an A in the input. Okay, I see an A in the input. Then I see a W, means some string on the stack, followed by A. So A is on top of the stack. This is what it means. So W, B. Okay, what does this denote? And W is in sigma star. B is a symbol, denotes B is on top of stack. Okay. For example, here there is a dollar, right? Then W, it means that W is nothing but epsilon, because there cannot be anything below dollar sign. Okay. Anyway, I see an A in the input, then I see a W followed by an A. Then what I'll do is I'll push an A. W A or A. This means I push A. That is what I was happening. As I keep seeing A's, I'll keep pushing A's. And now, if I see B at any moment in the input, and on the top of the stack, let's say I have a W followed by a B, means the top of the stack is a B. What does this mean? Top of stack is dollar. This means top of stack is A, and this means top of stack is B. If the top of the stack is B, then what do I do? Then I pop. How do I denote popping? I denote it by putting an epsilon. What does it mean? I remove B also. I remove B and push empty. What am I doing? Sorry. I see an A on top of this. If I see an A on top of the stack, I remove A and push epsilon. What is epsilon? It's empty. So it is as good as popping, right? It does not affect it. Right? In other words, we are popping A and pushing empty. So the net result is we are popping a symbol from the top of the stack. So this means we are popping a A. Okay, and then finally, if I see a B and then I see a W dollar, then what does this mean? I've already started seeing B. Okay, I've already started seeing B. I've already started seeing B, but still it's uh, if I've seen B, it means I'm good. If it means I'm good. Oh, okay. So Shashi says, so does it mean different number of alphabets will not be accepted, like A to the N, B to the N will not be? Sashi, do you mean for larger alphabets you will require a different PDA? Sashi, I mean you were explaining that it won't be accepted. Okay, okay. So yeah, there I. So that's why I asked the same. So it does not mean different number of alphabets will not be accepted, like A to the N, B to the M will not be. I mean you are explaining that it won't be accepted. So that's why I asked the same. So for example, yeah, this for example will not be accepted. You mean this you mean this I said it will not be accepted. That's what you're asking, Shashi? Yeah. Okay. Good. Yeah, this will not be accepted because I'll define my PDA to be accepting if my stack is empty. Okay. Actually, I made a small. Uh, so what I'm saying is not entirely true. That as soon as you see your dollar sign, you accept. Okay, that is not entirely true. Okay, as soon as you see your dollar sign, you accept. You will remove the dollar sign also. And another thing is we'll design the DFA so that it will be empty only if we run out of stack elements. Okay. Uh, so that's why I'm asking, because if I see it as a stack way, then it will not be so. Is it a general case of a special case? So that's what I'm asking, because if I see it as a stack way, it will not be so. It is a general case of a special case. If I see it as a stack way, then it will not be so. It will not be. So is it a general case or a special case? I do not think so. Okay, I'll okay, I'll do the complete construction. Then let me know. All right. The way you explain, like popping same number, and if some remain, there it will not be accept. The way you explain, like popping same number, and if something remains there, then yeah, exactly. So what we are working, yeah, exactly. What we are working with is acceptance by empty stack. So if something remains and I run out of strings to scan, if I run out of symbols to scan, then it will not be accepted. And if my stack somehow turns empty, then I'll accept. So Sashi, that is what is called acceptance by empty stack. There are two ways to define it, and they are equivalent. Okay, the other way to define it is um, acceptance by empty string. Okay, so I'm asking, is it a general case? Because then any string with different number of symbols won't be accepted, right? No, no, no. Okay, now I get it what you're saying. So you are saying that this is a special case for this problem. You are saying this acceptance by empty stack is special case for this problem, right? And therefore you are saying, oh, okay. No, Sashi, that is not right. It is not a special case for this problem. It is a general case. You can accept by empty stack for any problem, and they are equivalent. They are equivalent. For example, because see, because you can do this, okay? Because because see, I think the general way you've seen is acceptance by empty string, okay, which means acceptance by reaching the end of the string.
Sir,
Yeah, Bhuvan.
sir, we have four A's. For four B's, we need to pop up that. What about that one more B, sir? It is added in the stack, or what it do?
Oh
What it
yeah,
does,
yeah.
sir?
So for that case, so I come to this state, new state, and I see a B again in the input. Okay, I see a B again in the input. Then I see on top of the stack, if I have an A again, then I'll pop it, and this popping will keep happening. As you can see, this popping will keep happening as long as I see B's and A's. Okay, and I'll keep this as my final state. I'll keep this as my final state. Okay. Oh, not exactly. I'll keep. I'll make a transition now, such that if I see nothing, if I keep nothing, okay, and um, oh, sorry. Okay, there are no final states because I'm accepting with an empty stack. So I'll keep popping, and finally I'll see a dollar, right? If the number of, since I've inserted since I've inserted four A's, okay. So let's say in the first case I've inserted four A's, and now I'm starting to insert B's, and I'll keep popping each B for each A. Now if I see another B, it means I should accept, but you can see that by the time I have popped all these B's, all the A's are taken care of, and then the stack becomes empty. And so my PDA will easily accept it, simply accept it, because that is how I've defined my PDA. Okay. And in this case, there are more A's than B's. So for each B I see, I'll pop an A, then another B I see, I'll pop an A. But there are two remaining A's on the stack, right? And I've run out of my string. My string has finished. So what does it mean? I'll reject my string because my stack is not empty at the end. Okay, Bhuvana?
Yes, sir.
Okay.
That is okay. But
Okay.
if five B's are there for 4 A's.
Five, yeah. Oh, 5B and 4A's. Yeah, 5B's and 4A's. So it should not be accepted, right? So what I'll do is, so what happens for 5B's and 4A's? I'll push a dollar will be there. I'll push an A, then I'll push another A, then I'll push another A and another A and another A, right? All these are pushed. Now I'll see a B, then I'll pop an A. I'll see another B, and I'll pop an A. I'll see another B, I'll pop an A. I'll see another B, and I'll pop an A. And I'm still in this state. Okay, and there is one A remaining, and my string has finished. The stack is not empty, so I'll reject. Okay. Yeah. Okay. So Sashikant is. So I'm asking. Okay. So this is be quite easy to check whether a string is accepted by a PDA or not. That is true, Sashikant. But A to the N, B to the M is accepted by PDA, right? Yeah, that's true. But if I try it with stack way, it seems to not be accepted due to different number of A's and B's. So that's, oh, okay. So you mean, wait, Sashi, I want to confirm whether this language you are talking about, A to the M, B to the M, both are greater than equal to 1. Okay. So this is regular, and this is computable by a DFA, hence it can be computed by a PDA also. Right? Yeah. So, okay. I get it what you mean. So this does not. So the idea would be, if I keep pushing A's, what you I get it what you're saying. So if I keep pushing A's, and if let's say n A is more than B's, so I'll never reach the empty. So 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 what happens is, so yeah, that there I was. This was exactly what I was saying, that what I was talking about emptying is not exactly uh, correct, because what we want to do is we want to pop this dollar also at the end. Okay, what we want to do is we want to pop this dollar also at the end, and we want to check when the dollar can be popped. That is basically it. Okay, for example, if I see a dollar, so I keep popping, okay, out here, and someday I'll see a B and I'll see a dollar. What I'll do is I'll pop that dollar. Okay, I'll pop that dollar and I'll go to this state, and this is actually your real reject. What am I saying? So this is your I see a B, uh, and I see, okay, wait just a moment, and I stay at the state, and if I see, and I keep popping, and I see a dollar on top also, okay, and I see a B on top also, and I see, so I've run out of, okay, yeah, sorry. So if I keep doing this, okay, and if I see, I keep seeing B's, and I see a B, and then I see that I've entered an empty, I'll keep it at dollar. This is a reject. Okay, this is supposedly a reject. Okay, and if not, if I don't do that, okay, if I don't do that, and I don't see any string anymore, okay, and I see W and dollar, then I'll pop it. So this is the point where I'll reach an empty stack. Okay, so this is the point where actually I see an empty stack. So seeing a dollar is not enough to actually call it an empty stack. Okay, so wait, okay, you sent me a link, please check this. Okay, and n factorial is equal to m, and
Hello, sir.
yeah, yeah,
Sir,
I'm just
I have a doubt, sir.
checking the, yeah,
Um, we have four push operations means to pop up that we need a four pop operation.
four push, yeah, that's right,
Then we can say it is accepted.
right.
If we have a four push operation, the pop operation is five means it is whether what is uh, what we call this, sir.
If four push operations and five pop, this is okay, can you repeat that?
Sir,
Yeah, can you repeat that?
so like four A's, five B's, sir.
Okay, 4 A's, wait one moment, 4 A's, 5 B's.
Five,
Okay,
yes.
so what will happen here is I'll push 4 A's, right, onto the stack, and I'll start popping. Okay, and this, yeah, at this point I've popped everything, right, and this is the exact scenario. if I see a B, okay, if I see a B in the input, I'll have one B remaining, right, on the input, because I've pushed for each B, for 4 B's I've popped each of the 4 A's, right? So I'll have one B remaining. So for this A I've popped this, for this B I've popped this A, for this B I've popped this A, and for this B I've popped this A. I'll have one B remaining, and I'll have $1 remaining. So I'm saying there is B and there's dollar on top of the stack. Then I'll keep dollar on the stack.
Then we can say the string is accepted, sir.
No, the string will not be accepted because the stack is not technically empty. So the definition I'm using is that even dollar should be removed. So, but in this case, if it does not see anything, and since it's non-deterministic, I can use an epsilon here, transition, right? And on seeing an epsilon and seeing a dollar in the dollar, I'll pop. Okay. Yeah, Sashikant. But in A to the N, B to the N, it can case different push and pop, so that according to stack, it should not be accepted. But it's indeed accepted by PDA, and what is confusing? Okay. But in A to the N, B to the M, it can be a case of different push and pop. So then, according to stack, it should not be accepted, but it's indeed accepted by PDA, and what is going on? But the link I've shared shows that it's accepted.
Sir, if for 4 A's we have 4B pop-ups. Already we have reached the end of the stack.
Yeah.
Why don't we call this as accepted state, sir? Even though one more B is there, sir. One more B is there.
Even though one more B is there, because oh yeah, you're right. Sorry, another mistake I've done. Don't know what I was thinking. Oh, okay. So the DF is slightly wrong in this case. So if I see a B and I see a dollar, oh, it's still fine. That's right, you're right. This is not required. So instead, what is happening is, yeah, this is not required. That's right. And Sashi, yeah, one thing is, see, the y is A to the N, y is, wait one moment, y is A to the N, B to the M, where A is greater than or equal to 1 and B is greater than or equal to 1, accepted by a PDA. This is an example of a language where you do not need a stack at all, actually. Right. This is an example of a language where you do not need a stack at all. This is a regular language. A PDA is also a DFA. A DFA is also a PDA where I do not use the stack at all. Okay. So, for example, how do I do it using a DFA? What is the problem with this? My pen is... Okay, let's see. Huh? Yeah, okay, it's back. So yeah, Sashi, where was I? Yeah, the fact that A to the N, B to the N is a regular language is simply a case when you do not need the stack at all. Okay, the reason for the equivalence of see, empty stack is equivalent to empty string. Okay, why is this the case? The proof is as follows. If I reach the end of the string, okay, if I have a string and I reach the end of the string, then I can keep popping from the stack non-deterministically. As long as I see an epsilon, I can keep popping from the stack until the stack is empty. Similarly, um, if I have this is equivalent. I can define my term that way. Similarly, if I have an empty stack, okay, what I can do is I can non-deterministically look at all the symbols following it, and I'll reach the end of the string and then accept simply. So I mean that is the logic why it's so. What I mean is, don't get too much confused about acceptance by empty stack and acceptance by empty string. As long as the uh, general idea is same. Okay. Now the next thing I was talking about is this guy is regular. It is as good as having a DFA. Okay, and writing a PDA really does not need a stack for it. Okay, it does not need a stack for it. All it needs is actually that the fact that a to the n, the fact that I just keep seeing a's, then I keep seeing b's. As soon as I see the last symbol, what I'll do is I'll accept. If I do it by empty string, if I accept by empty string. Now let's say I'm talking about empty stack. Okay, let's say I want to talk about empty stack. A to the n, b to the n, and I want to accept this by empty stack. And n and m both can be anything. What I'll simply do is, as soon as I see an a, okay, as soon as I see a first, or as soon as I see nothing, actually, as soon as I see empty, okay, what I'll do is I'll push a symbol a here, and then I'll work as if I am working with a DFA. What I'll do is, as I'm seeing a's, I'll just keep seeing it. As I'm seeing a b's, I'll keep seeing it, and after seeing b's, if I see another a, then I'll reject. If I see another b, I'll reject, and so on. How do you design a DFA for this? As simple as that, right? Now, at the end, what I'll do is I run out of I'm in a accept state of the DFA, and then I run out of strings to see. Then I'll just pop that a on top of the stack on seeing epsilon, and then I'll pop that a from the stack, and then I'll pop the dollar from the stack. And you see, right, that actually inherently it does not actually require the stack to be used itself. This problem does not need the stack to be used itself because DFA does not need a stack. But I'm mimicking the DFA here in order to make sure that I'm accepting on an empty stack. I mean, I'm just writing this extra symbol a, and if that particular DFA simulation it accepts, then what I'm doing is I'm popping from the stack, and therefore I'll accept by empty stack. Otherwise, what I'll do is, if I want to accept by empty string, I don't even do that. I don't even push anything to the stack. I'll just simulate the DFA. I'll do the same kind of transition. I won't use the stack at all. I'll keep the stack contents as it is, and then I'll accept. So yeah. So this is the case when a to the n, b to the m is. Now, yeah, I'll have a look at the. So far, do you get what I'm saying, Sashi? So I'm looking, not completely, but I'm getting a little. Oh, okay. I'm sorry for the confusion, but what I mean to say is, in this particular example, a to the n, b to the n, where both can be anything, it is regular and you don't even need to use the stack. Okay, that is one thing. And the other thing is this particular language that, okay, I'll just check out this page where you have said this factorial, right? N factorial is equal to m. Um, So at the end, if the stack becomes empty and B is coming, or string is end and the stack is not empty, then we can say that the string is accepted on B. Yeah, but they follow the same thing, right? When B becomes, then pop one A from the stack each time, so that at the end, if the stack becomes empty, B is coming or string is end and stack is not empty, then we can see that the string is accepted by B. Well, the idea is the same, at least from what they are explaining, that B is coming at the end. Sorry, the string is ending and the stack is not empty, then we say that the string is accepted by. Oh, okay, I get it what you're saying. Okay, sorry, you mean that, yeah, sorry. So you mean that I think there is an issue with this page because they are saying that the stack is not empty, then the string is accepted by the PDA. Do you mean there is that is a problem here? There is this line that says the stack is not empty, then this is accepted by the PDA. The string is accepted by the PDA. Seeing it as a DFA was easy to get, but doing it with the stack looks confusing with me. Yeah, so thing is, do not focus too much on the low level of stuff. That is what I would say. As long as you know the operations, as long as you know what to push and what to pop, it is only of a matter of semantics. What kind of operations are allowed, and then you design the states and so on. Okay. And what in this particular Geek for Geeks page, I think that particular line is wrong. Because what they are claiming is if the stack is empty, non empty, then it accepts, right? Or what do they mean? It's written in a very confusing fashion. Okay, that particular line is very confusing. But yeah, at least till here, believe me. Okay, and so that is there. Okay, Bhuvana had also given me a list of questions. We'll address this now. Okay, Bhuvana, you there?
Yes, sir.
Yeah, we'll now do the questions that you've asked.
That
Okay.
4A's and
Yeah,
5B's.
Okay. And Sashikant, is there anything else regarding this? Let me know.
So also, sir, one more question.
Yeah.
Here to deterministic push down automata and non-deterministic push down automata is similar to finite automata, sir. It means that only one transaction.
Yeah, makes only one transition. That is one thing. And always remember that, is it possible? Can you share Turing machine transitions as well? Yeah, sure, Sashikant. Okay. Another thing is DFA is equal to NFA in terms of power, right? Bhuvana? But DPDA is not equivalent to non-deterministic PDA in terms of power. Okay, keep that in mind. I mean, there are languages that can be solved by PDAs, no non-deterministic PDAs, but not solved by PDAs. But when we say therefore PDAs, we always mean non-deterministic. Okay, when we say push down automatas, we always mean non-deterministic. And okay, now Sashikant is saying, if possible, can you share Turing? Yeah, okay, sure. Turing machine transitions as well. So Turing machines. So Turing machines, okay, have a tape like this. And that article of Geek for Geeks, can you explain the graph transitions of PDA? Okay, how much time do we have? Yeah, Sashikant, I'll try to have a look at it, but the other issue is that the article is written really in a confusing manner. But okay, let's see. Okay, Shashikant. Okay, so I'll quickly do this Turing machine thing. Okay, and because this bonus questions also I need to. What is this? Oh, okay, yeah, sure. Okay. Um, Now, so here it has a tape here. Okay, Turing machine has a tape, and the transitions look as follows. Okay, and on what does the tape look like? It has blank symbols, and so on. And actually, a Turing machine is a two-way infinite tape. Okay, but there is something called a left end marker, like this. The one tape Turing machine, what I'm talking about is as follows: there is a left end marker. Okay, there's, and the input is written here. For example, 0 1 0 0 1 0. This is the input, and I can write on this, I can read on this, and so on the entire tape, and it's infinite. Okay, so what this left hand marker makes sure that I know where the beginning of the tape is. Okay, okay. Now, see, again I'm repeating this, the amount of low level details is not actually required. Okay, but I'll explain that later on. But let me give you an example. And what do the transition in a what do the transitions in a particular Turing machine look like? It looks like this, that this we are in a state Q, and we are reading a symbol, um, let me call it S. Okay, if I am in a state Q and I read a symbol S, then I go to state, then I move left or right. Okay, and simply take a string and show it how it's accepted or rejected. That would be easy to get. Yeah, in the Turing machine example, right? I'll tell you, okay. And okay, so symbol followed by an S prime, okay, which is the symbol you're replacing it with, and then followed by a left or right, and the new state Q prime. Okay, so S prime is a new symbol, this is the old symbol or current symbol, and this is a new state. Now I'll show you. L is the following language. um, L is this language. W prime, W W example 0 1 0 0 1 0. Okay, 0 1 0 0 1 0. Or okay, first I'll do W reverse. 0 1 0 1 0 1 1 0 0 1 1. Okay, what is the idea? Okay. What is the idea? This is the input, 1 1 0 0 1 1. What is the idea? I keep, I have the left hand marker, okay, and I see the first symbol, it's a 1. Okay, the idea is I keep, and what I'll do is I'll mark this by a different symbol. Okay, I'll mark this as a X. I'll increase the alphabet. Okay, I'll mark it as an X now. Okay, and I'll keep moving right until I see a blank symbol. And once I see a blank symbol, I'll go to the left and I'll notice that, oh, this is also a 1. So I'll mark this as X. Getting it? Now what I'll do is I'll keep moving left and I'll see x. As soon as I see x, I'll go to the next, I'll go to the right and see that this is a 1. And now I'll mark this as an x. And what I'll do now is I'll keep going right until I see an x, then I'll move left and then mark this as x if it is a 1 again. So I'm matching it one by one. And then I'll keep moving left until I see an x again. I see an x, I move to the right and mark this 0 as an x. Then I keep moving right until I see another x and move left and then move x. And if I see that two x's are adjacent to each other, on moving to the left I see an x immediately. It means the two strings are reversals of each other. Basically, I am mapping like this and so on. I'm doing this mapping and this is how I'll accept. Okay, and let me know if you want to do it, me to do it in a transition diagram fashion also. I'll just briefly tell you the transition diagram will look like, if I'm in Q0 and if I see okay, first what I need to do is if I am in Q0, then I see a 1. Okay, if I see a Q0, then I see a 1. I'll go to a special state. Okay, then if I see a Q0 and then I see a 1, then what I'll do is if I see a 1, then I'll keep the 1 as, I'll mark it as an x. Okay, I'll mark it as an x, then I'll move to the right. Okay, and here I'll keep moving right. If I, as long as I see a 0 or a 1, I'll keep moving right, no problem. And I'll keep moving right as long as I see a 0, 1. But as soon as I see a blank symbol, okay, as soon as I see a blank symbol, then what will I do? Okay, I see a 0, then I'll write it as a 0 and move right. If I see a 1, I'll write it as a 1 and move right. And then I see a blank symbol, then what do? I move left. I keep the blank as a blank symbol and move left. Okay, as soon as I move left, what do? Since I need to see a 1 now, because I want to mark off all the 1s. If I see a 1, I'll mark off 1. If I see a 0, then I'll mark 0. That's what I do. And if I see a 1 now, if I see a 1 now, okay, no, not here, I'll go to a different state. If I see a 1 now and I mark that 1 as another x, okay, and then I'll do a left, and again I'll keep moving left, and then so on and so forth. This is how the transition diagram will look like. Okay, Sashi, is that fine? Okay, good. So, but now coming back to it, see, in advanced, I mean, studying Turing machines in a higher level, you do not talk about such low level processes. Okay, and even if you may have noticed in the NPTEL questions, you don't ask questions like these. This is very low level and we are not interested in questions like these. Okay, because of what is called the Church-Turing thesis, which says that any computational model is either less powerful or more powerful than Turing machines. We do not know whether this is correct or not, okay, but we have like 99.9999% belief that this is true, that Turing machines are the most powerful things you can create, most powerful realistic machine model you can create. Your computer is as powerful as Turing machines. So what it means is that any algorithm you create is as powerful as Turing machines. So always remember that if you're talking about computability problems and solving problems and checking whether you can solve it using a Turing machine or not, you can, instead of using Turing machines, you can always use algorithms, because that algorithm can be simulated by a Turing machine. Turing machines itself can simulate Turing machines. Okay, and algorithms can also be simulated by Turing machines. For example, if I ask you the following problem, okay, um, given a graph, okay, is uh, is it complete? This is the question, and you don't know how to do it using Turing machines, let's say, but you can also write an algorithm for it. No, actually, using Turing machines also, it is simple. You just look at the matrix and check if all the entries are ones. But let's say something like, if does it contain a cycle? Now this is more non-trivial. You need to look into the adjacency matrix at particular positions and indexing and so on. It's difficult, but using a C program you can easily do it. But using a Turing machine, it becomes much more harder. So that is what I appeal, that instead of looking at algorithms, okay, instead of looking at these problems as Turing machines, try to look at them as algorithms. Because once you try to solve these high level problems, okay, thinking about them in these low level manner, that zeros and ones and input tape and so on, okay, that becomes a bit tedious to think about. Okay. Yeah. So yeah. Now, is it, if possible, then please explain the graph as well, like what it means by a slash a, etc. This is the last question. Oh, okay. So let's see what they are using to denote. Okay. Um, okay. So they are doing the same thing. Okay, but instead of what I was what I was doing was this. Okay, if wz, okay, then if wz, then z a means I'm pushing a on top of the stack. W Z, then I'm pushing a on top of the stack. This is what this is what I was meaning, but there what they mean is a okay, or a z, means they are looking at the stack from this side. Okay, so it means that if if on seeing an a in the input, if on seeing an a in the input and I see a z on the stack, then push a z, meaning z is already there and a I'm pushing. Getting it? It's similar. It's just that I was looking from left to right and they were looking from right to left. So for example, and they were not considering this string w. Okay, for example, one transition looks like b comma a slash epsilon. This means if I read b in input, okay, and I see an a on top of the stack, okay, then I'll remove a and push epsilon. Similarly, before what I was doing, I was removing z, then pushing z, then a. Similarly, what I'm doing is removing a, then push epsilon. What does it mean? This means I'm popping a. This means I'm popping a. This is what it means. Okay. So no, in exam such questions come with similar graphs. So I want to understand how to read such graphs of PDA. Okay. Yeah. For PD, it is definitely there, and yeah, I don't mean that this transition diagrams are not important at all, and especially for things like PDAs and DFAs, they are important. What I mean is when you ask subjective questions about Turing machines in specifically. Okay. What I mean is when you ask subjective questions about Turing machines, especially. So, for example, if I ask you a question like, um, is the following is the language this 0 to the is the language, say, 0 to the 2 to the n, is this computable by Turing machines? And you may try to do it with this 0 1 trick and so on, but what I mean is you can just simply create an algorithm to do this, or at least implicitly understand that, okay, I'll just cancel this 0 and move left and move right and so on. That is what I was meaning. But of course, I do not condone that transition diagrams are evil. Okay, yeah. Yeah, so that is what I mean. Is that fine, Sashi? Yeah, okay. Okay, now let's look at. So, Bhuwana, these are too many questions. So, please tell me which specific ones you want me to address. Hello, Bhuwana?
Yes, sir.
Yeah, can you tell me which ones? So, I'll open
Last
here.
is assignment 9.
Um, okay, one moment. Hmm. Okay.
Assignment 9, 8th question, sir.
Assignment 9.
8th question. That is a number actually, sir.
Eighth question. Okay, wait. Oh, sorry. Eighth question. Okay, here, right? This one?
Assignment 9, 8th question, sir.
Yeah, this one, right? Can you see it?
No, sir. Yeah, this is, I think, this I have understood, sir. I think this is a different assignment. What is that?
Assignment 9. This is the eighth question. Bhuwana. This this is the eighth question from assignment 9.
Okay, sir. Okay, sir.
So this is fine, or should I explain this?
Yes, sir. You can explain it, sir.
Oh, okay. So the question is as follows. The question says, let primes denote the problem. Given a natural number n, output 1 if n is prime, otherwise output 0. Okay. One straightforward algorithm for primes is to check for divisibility by. Okay, I'll just screenshot this. Okay. Oh no. Okay, wait. One moment. Sorry. Sorry. I unshared my screen by when I took a screenshot. Okay. So I'm pasting it here. Okay. This is visible, right? So let primes denote the problem. Given a natural n, output 1 if n is prime, otherwise output 0. So please explain the PDA graph too. Okay. Sure, Sashi. Okay. After this, okay. Primes will give a 1 if n is prime and 0 if n is not prime. Okay. One straightforward algorithm for primes is to check the divisibility by numbers between 2 until root n. So this is a cleverer way than going 1, 2, 3, 4 till n. Okay. What is the most naive way to check if a number is prime? So what is a prime? It is divisible by 1 and itself. Only by this. only by 1 n itself. What is the way to do this? One way to do this is I divide by 2, 3, 4, 5 and so on till n minus 1, and check if any of these divide n. That is what I do, and if any of these divide, then I will not accept. But what it's saying is numbers between 2 and root n. So 2, 3, 4, 5 and so on till root n. Now this is slightly more cleverer, right? Any factor, okay, any factor that divides n will be within root n, because all the remaining will be multiples of these, right? All the remaining numbers between root n to n will be a multiple of 2, 3, 4 till root n. You can try this by yourself. So this I won't dabble into much, but yeah, this is another way. So check from 2, 3, 4, 5 whether it divides n or not till root n, right? So the algorithm performs order root n many division operations. Yeah, that is true, right? We check if 2 divides, we check if 3 divides and so on. So I'll be doing root n minus 1 divisions. So this is true. And the algorithm correctly outputs if n is prime. That is also true. I see nothing wrong with this algorithm. This algorithm has polynomial time complexity. Well, root n is nothing but n to the half. So it is order n to the half, and half is a constant. So yes, it is polynomial. So this is also true. The algorithm proves that primes is in P. This is false. But this must be surprising because, oh, okay, no. The algorithm has polynomial time complexity. This is also false, sorry. Why is this false? Now that is the question, right? It does not perform order root n many divisions. Yeah, it does perform root n many divisions, capital N, but not small n. What I mean by that is, let's say n is the input size, input length. And what is capital N? Capital N is the number given. But what is the input in? Input is in binary. So if my number n, I need to check whether it's prime or not, is 31. Okay. In binary, what will it be? In binary, it will be 1, 1, 1, 1, 1. Is it the case? Yeah. Yeah, 31 will be 1, 1, 1, 1. So as you can see, in decimal, it takes smaller space than representing it in binary. So in binary, how much space will it take? What is the length? Input length n is equal to logarithmic. If for any given number n, how many bits does it need to represent it? Log of n. Log of capital N, but which is nothing but log of root n. Now what is this? Log of n to the half, which can be written as half log n. Okay. What? Sorry, the input size will increase. It's the other way around. It's the other way around. Log n is equal to the input length. The input size will be log. Yeah. Right. Okay, I wrote the same thing again. Will be log n. Yeah. This is it. Now, what does it mean? The input size is. Input size is 2 to the n by property of log. This is base 2. Right. Input size is 2 to the n. So what does it mean? Algorithm runs in order. Oh no, I made a mistake once again. Wait, that given a number I want to represent n, I need log n bits. So to represent a number n, I need log n bits. So the input length is log n, which means, okay, input length is log n, which means n, so n is equal to small n is equal to log n, which means n is equal to the power n. Yeah, okay. Yeah. So to represent a capital N number in decimal, I need log n bits, capital N many bits, and input length small n is log n. Okay. So capital N is nothing but 2 to the power n. And algorithm runs in how much? Order root n time, right? Which is order root 2 to the n time, which is order 2 to the n whole to the half, which is equal to order 2 to the n by 2. What is this? This is exponential. So it is not of polynomial time complexity, and the algorithm does not prove that primes is in P. In fact, it's a very, very non-trivial algorithm. This was proved in 2006. It's called an AKS primality test. So it was a team from IIT Kanpur, Manindra Agarwal, Kayal, and Nitin Saxena. Okay, and they together proved that primes is actually in P. So this was a huge result back then. It won the Gödel Prize also. Yeah. Okay. So okay, there is a okay. Bhuvana is left. Okay. Yeah. Okay. Sashi, you want me to explain the PDA, right? That was there in the link. Okay. Yeah. So let's see what is the question. Nm greater than or equal to 1 and factorial is equal to m. Okay. It's not n factorial equals to m. That's what I was thinking, that this n factorial is a very difficult problem. It should be recursively enumerable. It's not n factorial is equal to n, it's n is not equal to m. So the question is a to the n, b to the m, and n is not equal to m. This is what they are asking, right? So no, don't go for the question. Okay, this one. This is a different one. This is the same DFA, right? Okay. Okay. So you just mean that you want the explanation for the graph. Okay, good, well and fine. So okay, what is the logic here in the graph? Okay, I'll draw it here. The same graph. Okay, I'll draw the same graph here. Q0. And A, and AZ, and B, A epsilon, and Q1, B, A epsilon, and epsilon, A, and B, Z slash Z, and QF. Okay, you can take the screenshot and paste. Okay, I could have done that also, you're right. Very stupid of me. Okay, but this is visible, right? Yeah, okay, good. So in the beginning it says, if I see a Z, okay, and on the input I have an A, then I'll do an AZ. Okay, this is what it means. So what does AZ means? This is the top two elements of stack. The resulting top two elements after, and this is the top element. Okay, next. Okay, I've pushed an A here. Okay, that is what it means. So this, in other words, yeah. In other words, we are pushing A there. So you can also view it as popping what is on the top and pushing what was on the top as well as something else. Okay, so Z was on the top before. Now we are popping Z and pushing against Z and A. Okay, next we have an A here at the top, and it says if you see an A, push A again, and until you see A's, keep pushing. That is what it's saying, right? Until you see an A and you see an A on top of the stack, keep pushing. Okay, so this means what was the string of the form A. Now something else will happen, something newer will happen only if you start seeing a B, right? So now you saw a B. What is it saying? If you see a B on the stack, if you see a B on the input, and on the top of the stack you see an A, on the top of the stack you see an A, then what do you do? Similar to before, what are you doing? You're popping Z and pushing A and Z. No, Z and A. Similarly, what you're doing? You're popping A and pushing an epsilon. This time you're not pushing an A. This is why it is as good as popping A. Getting it? So this is popping A. So you saw a B, so you'll pop A. Now what are you doing? You are same thing again. So this is also popping A. As soon as you see a B, you pop an A. As soon as you see a B, you pop an A. For each B, you keep popping A's until there are two cases. How long will you pop? Until you see that there is an A on top, or you see that Z is reached. Okay. Suppose you see that Z is reached, you keep the Z as it is. That is what it is. They are not popping Z. So this, the standards may change. Okay. Sometimes in some of the stack empty condition, you remove that $sign also. You remove that Z also. Okay. But they are not removing Z. This is as good as empty. So you see a B. Okay. And what you do? You see a B, and on top of the stack you see a Z. What does this mean? You see a B, and on top of the stack you see an Z, which means all the corresponding A's have been popped off. And if you see another B, it means that the number of B can never be equal to number of A's, right? Because the number of B is obviously smaller. Right? The number of B's is obviously larger. Sorry. So therefore because now the stack is empty, you accept. Next, the other case is you see nothing. You see epsilon. And you see an A. Then you don't pop that A, you keep it as it is. For example, here. You don't see a B. Okay, you see nothing, and you see an A. It means you've run out of B's, right? You've run out of B's. Furthermore, there are still A's remaining on the stack. It means the number of B's is less than the number of A's, because even after cancelling for each B's, there are still some A's remaining on the stack. You don't want those kind of strings. Therefore, I'm not popping anything. I'm keeping that A as it is. See, if you see an A, you keep that A as it is. I'm not popping anything. Why? Because I don't want those kind of strings. And since if I'm keeping that A as it is, the stack is non-empty, and therefore I'll reject once the string runs out. Clear? So is that clear, Sashi? Okay, and in both cases it goes to accept state. Yeah, this accept state, we are still doing acceptance by empty stack. So this accept state is not important. This accept state actually does not signify anything. Okay, now it's clear. Good. Okay, so we are at 8:26. So maybe we can do one more question. Bhuwana, thank you so much for that. Yeah, sure, Sashi. So we are almost out of time. We'll just do one more question. So Bhuwana gave a long list actually, so I'm really sorry that we could not cover all. Bhuwana, can you ask me one more question and then we'll solve that and we'll wrap up?
Okay, sir. In assignment 8, I have lost, sir.
Assignment 8. Okay, fine. Assignment 8. Okay, which one? Yeah, I have assignment 8 here. Which one?
Eighth question, sir.
8th question. Assignment 8, question 8.
Yes, sir.
Okay.
So,
Okay. So let me take a screenshot carefully this time. Sorry. Yeah, good. So, question 8. Okay, so here's the question. For any language L and a string W, for any language L and a string W, define LW as LW where you have the original language L union with W. Okay, for example, if let's say L is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on, and W is 101, then LW is just 101, 0, 0, 0, 0, 0, 0. So one additional symbol. Okay. Oh, sorry, one additional string. But see, since it's a union, W could already be contained in L, right? So for example, so this is example 1. Example 2 is the same L, but W this time is 0, 0, 0. So in this case, what is L? 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on. Right? So in this case, L equals L. So when W is in L, L equals L. LW equals L. Okay, so this is one observation. Now there are two statements. Okay, the first statement is L is Turing recognizable, then LW is Turing recognizable. The other statement is LW is Turing recognizable, then L is Turing recognizable. Okay, LW is Turing recognizable, then L is Turing recognizable. What does Turing recognizable mean? Turing recognizable means Turing recognizable means that if X is in L, then that machine M accepts, halts and accepts. So X is not in L, let's say this is not in the language, then M may not halt. Okay? M may not halt. So on the yes case, it definitely halts. In the no case, it may not halt. Okay. So now let's see. Statement P says L is Turing recognizable, then LW is Turing recognizable. P says L is Turing recognizable. So Turing recognizable and Turing Turing recognizable is nothing but recursively enumerable. Enumerable. Okay. So yeah. Now L is Turing recognizable. So if L is Turing recognizable, then what do you have? There exists a machine that says yes in uh, that says yes that says that halts when x is in L. This is given to us. So all we need to do is now, okay, we need to construct a Turing recognizable machine for LW. It's as simple as follows. What I'll do is, here is machine MW, Turing machine MW. Input is X. Okay. What I'll do is check if X, that input, is equal to W. Check if that input is equal to W. If it is equal to W, what should I do? It belongs to the language LW, right? So I should accept. So accept X and halt. Otherwise, what does it mean? If X is not equal to W, it means it is one of these other strings, no? One of these other strings. Before it was W, so I've accepted it, fine. It means it's one of the other W's. The other W's can be accepted by the machine for L. Because remember, L is Turing recognizable. And we are calling that machine, let's say M. Okay. So then what you do? Otherwise, run M on input W. If M accepts, it means it is in L. Then accept. On input, sorry, X. So for what kind of strings does this machine MW accept? It accepts for those X which is equal to W, or those X which is accepted by M and not equal to W. It accepts W and those X which are accepted by, and those X which are accepted by M. So which are accepted by, which is nothing but language of M. But what is language of M? L, right? W union L, which is equal to LW. So this Turing machine, and it will always halt for accepting when X belongs to the language, it will always halt. So this is Turing recognizable. LW is Turing recognizable. LW is Turing recognizable. So statement P is true. Let's see statement Q. Q says the opposite. LW is Turing recognizable, then L is Turing recognizable. LW is Turing recognizable, then L is Turing recognizable. So what does this mean? There exists a Turing machine M such that X is in LW, then if and only if M halts and accepts W. Okay, now I need to find the Turing machine for L. Okay, so what I'll do is, I'll have two particular cases. Suppose W is in L, then we already know that LW is equal to L, right? Then M, language of M, is equal to L, which is equal to LW. So this is already Turing recognizable. L is Turing recognizable because it's the same language, because W already belongs. Suppose W does not belong to L, then what do you need to do? We need to accept all those languages which do not equal to W. So we need to reject W. So here is the language. Here's the machine M prime, I will call it. Okay, and suppose W is an L, and okay, so I'll call this MW. Okay, so what I'll do is first I'll check whether it's equal to W. Input is X. Check if X is equal to W, then reject. 2 is otherwise what I'll do is run M on W on X, sorry, and if it belongs to the so if I'm on the language of the machine, then accept. So what is the language of the machine? It'll accept everything from LW except W itself. But what is this? Since W does not belong to the original language L, this is nothing but L, which means the language of this machine L prime is equal to L. So we've created a and this machine, as you can see, will always halt on the accepting condition. So this is Turing recognizable. So both P and Q are true. Okay. Yeah, is this clear? Bhuwana, Sashi?
Yes, sir.
Okay, good. Sashi? Yeah. Okay. Okay, with that, I think we've extended by quite a lot. So we'll stop the session. Okay. And yeah, please. So this was the last session. So I had a lot of enjoyment on teaching you guys this particular subject. And oh yeah, thank you, Sashi. Yeah. I'm glad you liked it.
Thank you, sir.
Thank you very much. Yeah, thank you, Bhuwana. Thank you, Sashi. Okay, then good luck for your, I think it's on the 20th. So you have one more day. Along with today, you have 2 more days for preparation. So I hope you guys do well. Okay. And I hope you like the subject. So we are all quite hungry at this point, I think. So please have your dinners and good luck. Okay. Thank you, guys. Good night.
Thank you, sir.
Good night. Yeah. Good night, Bhuwana.
Thank you.
Yeah. Good night, Sashi.